Okay, so now we're with this question, tension, and this tension question kind of emphasizes that tension in a string is constant throughout the string, right? Okay, so we're given this setup, right? Two objects, and they're connected by a string, and we're supposed to find the mass of the block B, right? So to find the mass of block B such that the sphere A is in equilibrium. So first, let's investigate the force body diagram of block B. So if block B has mass mb, then there's gravitational force of mg, and there's also tension of T. And because B is in equilibrium, right? If B is in equilibrium, right? If the whole system is in equilibrium, then B is in equilibrium also, right? So if for B to be in equilibrium, T must be equal to mbg, right? Mass of B, G. So with this, basically, that's all we need to care about B, because the moment we know the tension in the string, right? We know that tension is constant throughout the string, right? Tension is constant throughout the string. So essentially, the only rule of this string over here is to connect, right, the mass of B, right, to the physics of A. So when they ask us to find the mass of B, actually all they're asking us is to find the tension that keeps A in equilibrium. And yeah, so now we're essentially done with B. We can focus all of the physics on A. So A, we know that A is resting on a parabola, right? But a parabola is not nice to work with because when something is resting on a slope, right? We want to find the we want to find we want to find the parallel and perpendicular components, right? We want to break down the forces into the parallel and perpendicular components. So essentially, we need to find the gradient of the slope at the location of A. And thankfully, we're given the equation of the parabola, right, as well as the coordinates of that point. So if we're given, we basically need to take a derivative, right? We need to find the gradient of the tangent line of this slope. So we take a derivative, then derivative of y with respect to x will give me 5x. And if we substitute, uh, 0.4, right? X equals to 0.4 into the derivative, then we get 2. So we basically get at the tangent line, right? At point A, the tangent line over here has gradient of 2. And with that, we can actually find the angle theta, right? Because tangent of theta is just 2. However, one might be tempted to take the inverse tangent to find the exact angle theta, but that's not really necessary. And generally, it is recommended that you do not work with so many numerical values because it could lead to inaccuracies or it's just more tedious in general. So actually, with this gradient of 2, it's enough information to find um, the cosine of theta and the sine of theta directly, right? And the reason is because if we draw this if we draw the gradient 2, right, then we know that the rise over run is 2 over 1, right? It could be 4 over 2, but that will lead to the same results, but to keep it simple, we have 2 over 1. Then by Pythagoras theorem, this is 5, square root 5, right? So we know that cosine theta, right, is hence 1 over square root 5, and sine of theta is hence 2 over square root 5. So essentially, this is just expressing cosine of theta and sine of theta in terms of tangent of theta, right, without ever needing to find the value of theta itself, right? So this is how we derive trigonometric identities also. Okay, so point is, you do not need to know the exact value of theta, right? You've already found the cosine and sine, which is what we care about, right? So yeah, so now we know that object A is on the slope. We know that object A is on the slope, right? And we know the we basically effectively know the angle theta, right? So if this is mg, okay, I'm gonna need to subscript mag, right? Mass of A times g. What other forces are there, right? Of course, it's normal contact force, right? Now, question: is normal contact force equals to mag cosine theta? The answer is no, because we haven't accounted all the forces yet, right? If you if you if you take if you consider the tension right? Tension, you realize, is something like that. And it is at an angle of 60 degrees with respect to the horizontal. Okay, so with that knowledge, right? Um, normal contact force is not equals to mag cosine theta because tension helps tension contributes a small amount, right? Tension has a contribution to the perpendicular component of the force. So if we break down, so these are all the three forces, right? So if we break it down into their parallel and perpendicular components, um, um, we actually only need to think about the parallel components of force. And the reason is because you see that normal contact force, right? You see that there may seem to be there's three contributions the to the perpendicular component, right? These are the three contributions: the gravitational, the normal, and the tension, right? However, normal contact force only contributes to the perpendicular component of forces, right? Which means that, and we know from the nature of normal contact force, that it will always adjust its value to match whatever is necessary, right? To match it such that the net force perpendicular in the perpendicular direction is zero. So basically, this guy, normal contact force, will always adjust such that normal plus t perpendicular plus mag cosine theta is equals to 0, right? Normal contact force will always adjust its value up and down, right, to match these two. Okay, yeah, okay, to be more precise, this is minus over here. Normal contact force will always adjust accordingly, provided it can, right? Provided it never becomes less than 0. If not, the thing will lose contact. So essentially, we don't really need to care about the perpendicular component of the forces, even though equilibrium implies that, right, the perpendicular and the parallel components of acceleration are both 0, right? Acceleration in both for both uh axes are 0, but basically the perpendicular component is kind of handled by the normal contact force, right? So we don't need to worry about it. So all that we need to worry about now is the parallel component. So the parallel component is just mag, right? So if I highlight it in blue, the parallel components, there's this guy and there's this guy, right? So mag sine theta is equals to t um t and okay, so we need to find, we know that this is angle theta, so we need to find um we need to take t t cosine of 60 minus theta. Yeah, 60 degrees minus theta. Sorry for that slow thinking. So we can use the, if I refuse to calculate, the angle theta, right, I can use the cosine addition rules. Cosine addition rules tell me that cosine of A minus B, right? Cosine of alpha minus beta is cosine alpha cosine beta minus plus sine alpha sine beta. Okay, so I'm using the fourth rule over here, the fourth rule. Okay, so with that, we know cosine theta. The reason why I want to do that is because we know exact values for cosine 60 and cosine theta, right? And hence we never need to calculate things numerically. So MAG, if I take a look at the mass is 4 kg, right? And gravitational acceleration is 9.81. So all we need to do is substitute the values inside. So 4 kg times 9.81. Sine theta is just 2 over square root 5 equals to t, right? So what are these values? Cosine 60 is just square root it's just cosine 60 is just 1 over 2. Cosine theta is 1 over square root 5 plus sine 60 is square root 3 over 2. Sine theta is 2 over square root 5, right? And from here, I can solve for t. And the value of t is, give me a while to punch the calculator. The value of t that I got is 35.160, right, to 5 SF. And of course, this has units of Newton. Okay, so so that's the value of tension. And just now we said that T is equals to MBG, right? Remember we considered the force body diagram on G, there's MB, G, and T. So if we substitute that in, right, we can get that MB, mass of B, is just T over G. Equals to T over G equals to what we got, divided by 9.81. And we get 3.58, right? That's 3 SF. And of course, the units is kg. Yeah, and so that is C. And so the answer is C. Okay, so that's how we do this question.